Hi everybody. This lecture we're going to explain how to solve circuits including diodes working as a rectifier. Before we do that, just let's review the characteristic of diode. Last lecture we explained the diode current voltage characteristic. And to do that, we did the two axes. One for the voltage across the diode, and the other one, the current in the diode. We observe that when we increase the voltage from 0, it doesn't start to conduct till it reaches 0.7 volt. And at 0.7 volt, you'll start to see that the current increasing rapidly. However, if it's reverse bias, you find that the current is almost 0 till you reach the voltage breakdown and then start to increase rapidly the current. So that's the characteristic for the diode. That's when forward bias, and that's when it's reverse bias. Forward bias, that's when the diode connected such that the positive polarity of the battery connected to the anode of the diode. And reverse bias when we connect the diode such that the negative polarity is connected to the anode. That's reverse bias, and no current will conduct. This curve in the forward bias, it can be expressed mathematically as exponential. So to solve it, it's a little bit involved. Let's make it simple. To make it simple, there's a representation for the diode as this is the forward bias, and it's connected in a way that the positive polarity of the battery is connected to the anode of the diode. And we can represent it as switch closed. So it's like a short circuit. So the voltage across the diode is equal 0, and the current will increase rapidly according to the voltage. If you represent it in this way, an IV characteristic, it will look like that. In the forward bias, along this line, this is a voltage across the diode, and this is a current across the diode. So you can see that the voltage always 0 across the diode because short circuit and the current is increasing. However, if you do it reverse bias, when you connect the diode as negative and positive, it will be represented as an open circuit. And when it's connected like reverse bias in this way, so the current will be equal 0, and the voltage across the diode will be the same as the voltage of the supply. If it's 1 volt, it's 1 volt, 2 volt, 3 volt, but in the reverse direction. So you'll find that it's going in this direction, but the current is 0. That's, the simple modeling for the diode. We call it ideal diode model. Let's take an example. We have a diode connected to 2 kilo ohm, and we have 10 voltage. find the voltage across the load, find the voltage across the diode, and the current in the circuit using ideal model. Okay, solve this one. Since the 10 voltage, the voltage of the bias is greater than 0, so the diode is on. And since the diode is on, we can represent it as a short circuit. Be like a wire. And the voltage across the load, V output, it will be equal to 10 volt because this is short circuit, so the output voltage will be equal to 10 volt. And the current will be equal to voltage, which is 10 volt divided by resistance of the load 2 kilo ohm, so we'll have 5 milliampere. And the voltage across the diode will be equal to 0. And the current in the diode, it's the same, the current of the load, because it's series, so it will be 5 milliampere. So that's when the voltage is equal to 10. Let's now have another example, and we'll flip this voltage. So I'll say that that's the diode, that's the resistance 2 kilo ohm, and the voltage will be reversed. So the negative polarity is connected to the anode. So it's going to be reverse bias. And since it's reverse bias, the voltage is less than 0 and the diode is off. When the diode is off, it will be like an open circuit. And that's your load. And that's the source. So the current is equal to 0 because it's open circuit. So if the current is equal to 0 ampere, so the voltage output R times I, and I equals 0, so the voltage equals 0. So the voltage is equal to 0. So what is the voltage across the diode here? Just apply Kirchhoff voltage law. That's the voltage across the diode, and that's the voltage across the load, which is 0. And you have a battery here, 5 volt. So the negative connected to the positive, so you are adding. So we'll say 5. That's applying Kirchhoff voltage law. 5 plus VD, and this is the voltage equals 0, so it will equal 0. So VD is equal minus 5 volt. So the volt will be equal to minus 5 volt, and the current in the diode, because it's open circuit, it is going to be equal 0. That's exactly like the characteristic we just mentioned here. So we are working here. That's 10 voltage, and the current is equal 0. And the first example, we have the voltage across the diode was 0, and the current was 10 milliampere. Okay. Now let's be more practical. We'll have something called practical diode model. Well, it doesn't really start from 0 to conduct. Actually, you have to overcome the barrier voltage, which is equal to 0.7 volt. So what about if we move this line to 0.7 volt? So that here, 0.7 volt. So to be like a straight line at 0.7 volt, it means before 7 volt, the current is 0, no conduction. And of course, when it's reverse bias, it's going to be off. So the diode, when it's reverse bias like that, we say that the current is equal to 0. And the voltage of the diode, it's increasing negative in the reverse direction, but the current doesn't increase. But when you have the forward bias here, what does it mean, forward bias? It means you have the diode and you are putting positive voltage here. That's forward bias. Is it going to be on? Is the diode going to conduct in the forward bias? We'll say now forward bias, to make the diode conductive, you have 2 conditions, not 1 condition. So we'll say the condition for conduction in forward bias, two conditions. Number one, forward bias, you have to connect the positive to the anode and negative to the cathode. And that's what's happening. But it's not enough. The second condition, it has to reach 0.7 volt. And the voltage bias should be greater than 0.7 volt. Now I have two conditions. An ideal model of diode was not like that. It was enough just to have forward bias, and you don't have to have 0.7 volt. Now we have to have 0.7 volt. In this way, the diode, when it's conductive, it will be represented by an ideal diode plus a battery of 0.7 volt. And so when you have load, let's say 2 kilo ohm, what about if you have here 0.5 volt and it's forward bias? But because you have 0.7 volt as a barrier potential, here we're saying that it's not going to be conducting. Diode is off, it's not on, because the voltage of the supply here is less than the barrier. So you got to have more than that. Let's take now 10 voltage example. So if you have the diode and 2 kilo ohm, I will make the same example, and you have 10 volt. Now I want to use practical diode model. It's off. No, it's on. Why? Because the 10 voltage bigger than the 0.7 volt. Because this one, to represent it, we're going to add a potential in this direction, 0.7 volt. So what is the voltage across the load? Well, this will be like a short circuit. You have 0.7 volt, you have 10 voltage, so the voltage across the load is not going to be 10 volt only. 10 volt minus the 0.7 volt. So it is going to be equal to 9.3 volt. And the current is going to be equal to 9.3 volt divided by 2 kilo ohm. It's equal to 4.65 milliampere. And will be the same, the diode current is going to be 4.65 milliampere. What about the diode? The voltage across the diode, by the way, this is the whole diode. Okay? Remember the characteristic like that. So the voltage diode, the voltage across the diode does not change. It's 0.7 volt. So it's going to equal 0.7 volt. So that's, because it's on. And you can verify this value by looking at the voltage here and the voltage here. You find the difference, 0.7 volt. Let's take an example when it's off. If you have the diode and 2 kilo ohm and you have reverse bias, it doesn't matter now for off, it's a practical model or not practical model. Why? Because when it's a negative voltage, it's just, it's the same. The current will be zero. So just to be like an open circuit. You just make this an open circuit. And the current will be equal 0. The output voltage will be equal 0. The voltage across the diode will be equal minus 10 volt. And the current of the diode, of course, equals 0. Just like the other case. So when you have ideal diode or practical diode model, in off is not, there's no any different. The only difference in the on. Okay. Now just let's take another example. Rectifier, but we are going to take the first case, half wave. So half wave rectifier, what does it mean? It means if you have the half wave rectifier and you have the input like sine wave, the half wave is going only to take the positive cycle, but the negative cycle is not going to pass it. And so we take the third one, and it continue like that. This is the half-wave rectifier. And if you want to find the average value, you can find the average value easily. Let's just take one here. Oops. So only they have the cycle starts from 0, pi, 2 pi, and that's the maximum, because I mean the input was equal to V maximum sine omega t. To find the average value, you will say it's equal 1 over the period, which is what, 2 pi, the period is equal to pi, and the integration from 0 to pi, the voltage out. That's the rule to find the average. So it will be equal to 1 over 2 pi, and from 0 to pi, from pi to 0. But from pi to 2 pi, that's the whole cycle. So, but from pi to pi is equal 0, so you don't have this integration, so you have only from 0 to pi. The equation from 0 to pi, it's a sine wave, so it's equal to Vm sine theta d theta. So it's equal 1 over 2 pi V maximum, and the integration of sine will be minus cosine theta and pi 0. So it's equal to V maximum over 2 pi minus cosine theta. You can write cosine theta and then get rid of the negative sign by flipping the limit. Instead of 0 to pi, from pi to 0, is equal to V maximum over 2 pi cosine 0 minus cosine pi. V maximum over 2 pi cosine 0 is equal 1, and cosine pi is equal minus 1. So it will be equal to V maximum over 2 pi times 2. 2 cancel 2, so it's equal V maximum over pi. So the average voltage of the output in half-wave rectifier, it's equal to V maximum over pi, and 1 over pi is equal to 0.318. So that's the average value of the half-wave rectifier. The question is how to make the half-wave rectifier. Half-wave rectifier simply is made by a diode and the supply sinusoidal, that's Vs, and Vs is equal V maximum. Let's take an numerical example here. (15) sine omega t, doesn't matter sine or cosine, and you got the 2 kilo ohm, and you want to find the output, and you want to find the voltage across the diode. Now we have two things. First, we're going to have positive cycle one time, negative cycle one time. When you have positive cycle, that will be conducting, and the all positive cycle will come out by the same magnitude, which is equal 15 sine omega t. And when it comes negative cycle, it will be reverse bias, so it will be 0, and then it will continue like that. So the V output, we can describe it as equal to 15 sine omega t from 0 to pi, and equal 0 from pi to 2 pi. and then we continue. If you want to find the average value is equal V maximum over pi, which is equal 15 over pi. Or you can multiply 0.318 times 15 and you get the result in volt. To find the current, you just divide. When you find first the current as a function of time, it will be the same as the voltage output here, but divided by 2 kilo ohm. So if you divide 15 by 2, will be equal to 7.5 milliampere sine omega t, and this is only from theta 0 to theta pi. But from theta pi to 2 pi, the current is equal 0. And the average current, it will be equal to 7.5, which is the maximum, milliampere divided by pi. You get the average current. What about the diode? Well, the diode, when it's conducting, the voltage is equal 0. When it's not conducting, it will be open circuit. Let's have a look at it. When it's conducting, that one was the positive cycle. That when it's on. So the voltage will be equal 0. When it's not conducting, it's like an open circuit. And that's, when it was negative. So the voltage across the diode is equal to minus the voltage that we have here. The voltage, because the current is equal 0 and the voltage is equal 0. So the voltage across the diode, it's the same as the voltage of the source will be applied in it. Okay, so minus Vs, which will be equal minus 15 sine omega t. So the maximum voltage will be 15. The peak inverse voltage is equal 15 volt, or the maximum, the peak. So when you buy diode, you have to buy a diode that can stand with the reverse bias 15. You buy one more than that, okay, because this is the peak value. So that's the analysis of the half-wave rectifier when it's practical model. What about if it's not practical? When it was ideal model. What about if you use practical model? When you use practical model, we know that there are two conditions: be forward bias and the voltage greater than 0.7 volt, as we did in the DC exactly. So when you look for the sine wave input, that's the 15, minus 15. But there is 0.7 volt that you should compare with it. I just make it bigger just to make it clear. So the voltage of the source to conduct, it should be greater than 0.7 to start the diode conducting. So it will not start from 0. It will start from 0 if we are using the ideal model of the diode. But practical model of the diode, it means that you have to have the voltage overcome the barrier voltage, which is 0.7 volt. So it will start conducting from this point. But before this point, the voltage of the source or the supply, it is less than 0.7. So it will not conduct. For example, when the sinusoidal wave starts to increase, it starts from 0. When you have 0 voltage, it's less than 0.7. It's not conduction. When you have 0.1, 0.2, 0.3, still less than 0.7. Once it reaches 0.7, it starts to conduct. So it will start to conduct when it's above. But once it go again below 0.7, it will not conduct. No conduction here, no conduction here, no conduction, till it reach again 0.7, start to exceed, then it start conducting. So when you look at the voltage output at this point, if you say this is your 0 and this is your 0, I mean the 0 by this point, and this is the 0 here. So it's not going to be like that, no. It's between these two zeros, so it will be like that. And the magnitude is 15, but there is 0.7 here, so the maximum here will be like 15 minus 0.7, which is equal 14.3. And then it's off till again go at this one point. Will be 14.3 maximum. So that will be the voltage across the load. So it's not conducting the whole period from 0 to pi. No, it's less than that. It's a little bit after 0, and it will become 0 before pi according to the 0.7 volt. So that's the voltage. So you can say that the voltage maximum across the load, it will be equal to 14.3 volt. That's the maximum across the load. Accordingly, you can find the current maximum across the load. You divide by 2 kilo ohm, 14.3 volt divided by 2 kilo ohm, 7.15 milliampere. That's the maximum load current. But the load current will look like that, but the amplitude is different, 7.15. If you want to find the average, it will be approximation, not exactly. You can use the same formula, but it will be less than. So you can say that 14.3 divided by pi. That's approximation, not exact. I will be given the homework, how we find the exact formula. What else we want to find? We want to find the voltage across the diode. Well, when it's conducting, when the diode conduct, we know the answer, that the voltage across the diode will be 0.7 volt. But what about when it's off, when it's not conducting? Okay, so when it's conducting, you got to sketch the circuit like that. And this is the load. The voltage should be equal 0 because the current is equal 0. And that's Vs. So the voltage of the diode is equal to minus Vs. Minus Vs. And is not conducting from this, the all yellow part here. Let's just make a different color, tell you when it's not conducting. Change the color here. Is not conducting on this blue region. So this voltage will be across the diode, the blue one. The blue one will be the voltage across the diode. The maximum will be 15 volt. So the maximum reverse voltage across the diode is equal 15 volt in the opposite direction. So when you buy a diode, you have to make sure that your BIV is greater than 15 volt. So that's the solution of the problem of half-wave rectifier when you have practical. Now let's go to another topic, full-wave rectifier. And that will be the last one. The full-wave rectifier will be like, you have the sine wave, you have positive, negative, positive cycle. The output will let the positive to pass through it, and the negative will flip it up and rectify. So now we are in a better situation. If you do the integration as I proved the first one, it will be the same. Remember that the average voltage of the half-wave rectifier was equal to Vm over pi. Now, you have extra. So it will be the double, because we're missing the half cycle in the first one. So now it will be 2 Vm over pi. That's when you have the full wave rectifier. You can round this 2 over pi. You can write it like 0.637 V maximum. That's, I mean, when have the average value. Okay. How you do that? How you do the full wave rectifier? There are, I mean, 2 ways. There is something called center tap transformer, and there is one called bridge. Just I will go for the bridge. How we do the bridge? I will do the bridge in a simple way. Let's say that you have the source here and changing positive and negative and so on. The bridge, I will just make like a square here, and I will put the load inside. And then I connect one terminal by the first corner and the other corner by this one. Observe the corner that where I put the resistance of the load, I don't connect it to the supply. Now let's see. When you have the positive cycle first, so the positive cycle, it means here is positive and that's negative. I will choose different color. Red for the positive cycle. Positive, negative. So the current will go from the positive and go here. You want to go to the load. So I will put diode in this direction. I'm just showing now how you design by yourself the bridge. And the current will go through the load in this direction. You want to go to complete the cycle, it has to go in this direction, right? So you put diode in this direction. And go to the negative. So you make the 2 diode parallel like that, and this is their anode, their cathode. Now let's go now for the other cycle, the negative. Choose different color for the negative. Let's say green. So the negative will put like so it will go. So it wants to go this direction, so I put that in this direction. And then it go through the resistance. Observe that it's going in the same direction of the resistance. And then it go back here, so you put the diode in this direction. You go the negative. It finishes the cycle. So this is the bridge. That's diode 1. That's diode 2. That's diode 3. And that's diode 4. Diode 1 and diode 2 connect when they have the positive cycle, and diode 3 and diode 4 when you have the negative cycle. So that's, I mean, how it works. Let's have an example. I will take just a nice drawing here. Let's say that you have resistance is equal to 2 kilo ohm, and the voltage of supply is equal to 15 sine omega t. And you have silicon. First, we're going to use ideal diode model. Okay. So when you go for the red one, the diode D1 and the resistant, and diode 2 conducting, but D3 and D4 are off. Okay. So I will just I will sketch it like that simply, our square. And this is the resistance 2 kilo ohm. They are conducting, the one here. I mean, let me just put it in this way. And the other one, this direction, yeah. So this will be off, and this will be on. This will be on, and the other one be off. So I need to find the voltage for any one of those, but I will erase it because off will be like open circuit. But of course, this is conducting, and this is supply. And we know that the current will go in this direction. Okay. So if this one like a short circuit, no voltage drop, no voltage drop. So the voltage across the load, it will be the same as the voltage of the source. So the voltage across the load is equal 15 sine omega t. And the current in the load will be equal 15 sine omega t divided by 2 kilo ohm is equal 7.5 milliampere. That will be the voltage and the current. Okay. And the same thing, you can do the same thing when you flip the supply. But let's just, I want to find the voltage across any diode that they are not disconnected, like D3 and D4, any one of them, because they are equal. Let's say what is the voltage across D4. That's why I left the polarity D4. You can apply it by taking any closed circuit. I will take this circuit. I will mark it by orange color, because Kirchhoff law has to be like, a closed circuit. Okay, I'll take this circuit. So you have the voltage across the diode D4. This is 0 because short circuit, and you have the voltage of the supply. And the negative is connected to the positive. So will be V across the diode 4 is equal to minus the voltage of the supply. Minus the voltage of supply. So it will be like minus 15 sine omega t. And so the maximum voltage across this diode will be 15 volt. That's important to know the PLV 15. So I know now, the voltage across the diode, any diode when it's off, is equal the voltage of the supply. So the maximum will be equal to VSC maximum, which is equal 15 in the reverse bias. Okay. We need to find the average value. Okay, the average value will be simple. The voltage will be equal in 15, that's the maximum, times 2 over pi, or time the number that we agree about, 0.637, and you find the average voltage. The same thing for the current will be 7.5 milliampere times 0.637 volt. That's, when diode is ideal. What about if we do the practical? Okay. When you have practical diode model, and we'll take this circuit when it's conducting, but the diode will be now represented by back EMF. I'm sketching diode D1 and D2, and that's the resistance. This one is off. VD4, D4, the same thing. And then connect to the supply. First of all, they will not conduct when the voltage just is positive, right? The voltage has to exceed the barrier potential. But look at this tricky thing. Okay. This need to have the voltage should be more than 0.7 and should be more than 0.7. So the output voltage here, if you look at the output at the load, it's equal to the voltage of the supply minus 0.7 of the first diode and minus 0.7 on the second diode. So the output voltage in this case, it's equal to 15 sine omega t minus 0.7 minus 0.7 multiplied by 2. So it's equal 15 sine omega t minus 1.4. I'm sorry. Yes, 1.4, 0.7. So it'll be less. So that's, now the voltage, okay? That's the voltage output. The voltage output peak value, maximum value, would be equal 15 minus 1.4. That will be 13.6 volt. Okay, because you got two diode conducting here. It's very important. And now let's find the peak inverse voltage. we have to do closed loop for Kirchhoff voltage law. So I mean, I'm going to take this one. So what do you observe? It's the same like the other one, except now the diode is not ideal. The diode is represented with 0.7. So the voltage across this diode is not only the voltage source and the 0.7. So the peak inverse voltage should be equal to Vs plus 0.7. The maximum Vs is equal to 15. And this 1.7. So the maximum 15 plus 0.7. So it will be 15.7 voltage. That's the reverse. Okay. So we have to be careful about that when we are using the ideal model or practical model. I hope that you understood it, and if you have any question, please send it to me to do it together. And thank you.